Hey guys, Buildzoid here, and, well, this video would be short if I didn't want to do story time out of it. So, story time. This is a GTX 680 I picked up, and I picked this card up for a few reasons. Basically, I wanted, well, still want to, and will kinda do, a modification series on this card. So we already did some, like, cap modding on this card, and I talked basically, well, I used this card for doing a bunch of capacitor testing. Not that it was particularly useful, because basically the only thing I learned about this card is that on this card, if you add a lot of capacitance, it overclocks better. And what do I mean by a lot of capacitance? Well, let's see. This right here is 1, 2, 3, 4, 5, 6, 7, 8, 9 capacitors. These are 8-pack, and they're 820 microfarads each. When I was testing cap mods on this thing, I ended up with, I think, 20 Nichicon and other capacitors, because at that point I was just desperately trying to get more capacitance on the card. Um, basically the end result was that I was using like 1,500 microfarad Nichicons and 2,000 microfarad Ruth electronic caps, and also some like 470 microfarad SMD polymers from Panasonic. So big mix of capacitors. But the main goal was, this thing had like 40 plus thousand microfarads on it before it started to overclock. Well, like to pick up some 20 something megahertz. I think it was like 26 megahertz. Better overclocking after adding 40,000 microfarads of capacitors, which makes, like, that makes zero bloody sense to me. Okay, it should not work like that. You shouldn't be able to just stack and stack and stack and stack capacitors, and the card just keeps, like, it's not like it even kept, because it scaled really badly. Like, you needed 20,000 microfarads for that first 12 or 13 megahertz. And then the next 13 megahertz was another 20,000 microfarads. So I guess if you put 60 on this, it's going to do So I guess if you put like 100,000 off the back of this, which at that point you're talking supercapacitor size, it might actually do 1,300 core. And that really shouldn't, but that's what the trend seemed to indicate at that point. Nonetheless, the stock capacitance on this thing is barely... These are 820s and there's 9 of them, so... you know, it's like 7,000, like slightly over 7,000 microfarads that you get on this stock. And I was packing like several times more onto the back, which was just like, I don't know why that worked. Like, honestly, I have no idea why that kept working. Like, I would have thought, like, at some point it would just stop. And the funny thing is, like, I intentionally tested the same number of smaller capacitors to check if it was just like a, you know, just putting enough capacitors in parallel lowers their ESR and their ESL, and basically you get better filtering out of it. So I tried smaller capacitors in equal quantity in parallel, and that didn't do a damn thing, because they were too small. And so it's just like, this card loves tons of capacitance for some reason, which makes zero freaking sense. Like, zero. Okay? It should not work like that. At least you should not, like, there should be a point after which adding more capacitance doesn't do anything, and I didn't manage to hit that on this card, which is kind of concerning in my opinion. Anyway, so that was cap modding. The other thing about this card is that it has this voltage controller right here, which is an NCP4206. And the NCP4206, it's a on-semiconductor voltage controller. It has 6-phase output, up to 1.5 megahertz switching frequency. The reason why I wanted this specific voltage controller is because 12, who's a Russian overclocker, which his name is _12_, so that's if you're trying to look him up on HWBot. He's a Russian overclocker. He overclocks mostly on phase change. He also does liquid nitrogen and dry ice on occasion, but he mostly does phase change. And his, I guess, overclocking goal is to just overclock all the graphics cards or all the hardware. I'm not sure. Like, most of the time what I see is that he's working on some graphics card, and I think he's run out of CPUs. That's why he's working on GPUs now. Basically, he has 2 phase change units. He runs a high-end desktop Intel CPU on phase change, and then he runs a GPU on phase change, and he just goes and smashes all the benchmarks on that setup whenever he can. Because, of course, there's some GPUs like the 680 where all the top scores are on liquid nitrogen, so obviously turning up with phase change isn't going to really work out for you. But nonetheless, where he can, he basically, like, if you're benching, like, kind of oddity hardware or just not very popular GPUs, there's a pretty good chance that all the records for that GPU belong to 12. Just kind of what he does. So he sent me a message because he had a 7950 from Sapphire, which I think had a 4-phase VRM using this voltage controller. And the problem was that VRM was shutting down, and it was shutting down because of overcurrent protection. It was cooled well enough, it just kept shutting down because he was overloading he was pushing too much current through it once he went above 1.35 volts. So, I get sent the datasheet for this voltage controller, and there's a really interesting way to actually modify the current limit on this voltage controller, which is why I wanted it, because it's, like a lot of other cards, it would just be like a volt mod, and then we wouldn't do any, like, I wouldn't want, well, I have current modded a Vega. It sucked, so we're not going to go over that. But this thing's actually relatively easy to current mod, so I wanted to cover it because the VRM actually has built-in current protection. It's not just relying on the shunt resistors scattered around the PCB that the card has. Interestingly enough, this does have shunt resistors for current monitoring of input, but there's no INA 3221. So I'm not sure how this card is managing its current limit, but nonetheless, I'm just going to short all the shunts out because this is a 600 series, and these shouldn't have that safety feature that the 10 series has, which prevents the card from clocking up into 3D clocks if you short out all the shunts properly. Yeah, so basically this thing has an interesting OCP mod that you can do on it, and I wanted to show people, so I bought a card with it. And actually, what the 7950, after he modded the overcurrent protection, he blew up the VRM because it was a 4-phase. So yeah, he blew up the VRM, ended up e-powering the card. So yeah, but I don't think, well, actually, we might be able to blow up this VRM as well, because let's get into this VRM. This is not a reference NVIDIA VRM, which is actually really surprising because the card comes with this heatsink, right? You'd think that would be a reference PCB hiding under a non-reference shroud, but that's the heatsink, which is, I mean, it is a 680, so it's not a particularly hot running card, but this is a pretty crappy heatsink. I mean, 2 heat pipes and, well, fins on top. It's not actually, like, for a 680, it's actually fine. I'm surprised that this is like one of the few blower cards where even at relatively acceptable noise levels, it doesn't get that hot, which just testimony to how efficient 680s are, I guess. But yeah, so, you'd expect a reference PCB with the heatsink that this has, but no, this is an actual 6-phase. Now, the reference PCB, technically speaking, for a 680 does have a 6-phase VRM layout. It just doesn't, usually, it's configured for a 4-phase, like 2 of the phases aren't actually placed on the board in production. This is a proper 6-phase. It's also not using discrete MOSFETs, it's using power stages, which is why you see only 1 chip per inductor. So these are Fairchild semiconductor power stages, each rated for 45 amps. End result, this whole VRM has a maximum current throughput of 270 amps, which is not that high, but, for air-cooled and water-cooled overclocking, it's actually fine. And at stock, it's really efficient. So, let's go through the power figures for this thing. Assuming 300 kilohertz and 6-volt gate drive, which I don't think this card actually has, unless this LDO is 6 volts and not 10, in which case this is less efficient and that is more. But anyway, I was lazy. I didn't want to scale the calculations for lower gate drive. So we're just going to say it has 6 volts, even though it probably doesn't, because there's nothing actually anywhere on this card that, except this LDO, that could possibly be making 6 volts. And that's probably making 10 for this, because this on 5 volts or 6 volts is going to suck. Anyway, so VCore VRM, 300 kilohertz switching frequency, 6 volts gate drive. For stock clocks, so, 680s boost to around 1090, 1100-ish megahertz on stock. At 1.175 volts, you'd be looking at about 140 amps going through the VRM, and for that, it'll produce about 13 watts of heat, which is really nice. That's really not bad. Now, if you start to push the card and go up to, say, 1.25 volts and manage to hit, say, 1300 megahertz core clock, which I don't think this card will actually do, considering on 1.175, this thing barely does 1200. yeah, this card's not really a great 680. I don't particularly care. I bought it to basically do experiments on. So, you know, so for the 1300 megahertz, 1.25 volts, this should push about 185 amps through the VRM, producing about 20 watts of heat. So that's still very much handleable, especially considering that this thing has it has thermal pad spots for the actual VRM. So the VRM sinks its heat into this great big, not a heat sink, because quite frankly, this has zero surface area, but it does at least dump well, it's not zero surface area. It's more surface area than those MOSFETs, but as far as being a heatsink goes, this doesn't actually, do much of that. Well, actually, it does sink heat, it just doesn't dissipate it. So, heatsink by definition there. So yeah, but, it is cold. And 20 watts, that plate should actually dissipate just fine. That shouldn't really be a problem. Now then, if you start pushing it on water, things start to get a bit concerning, because 1.45 volts and 1450 megahertz, which I think is achievable for a 680. Again, I don't generally do NVIDIA cards. I've not really paid much attention to the 600 series up until very recently, so, I think 1450 is actually in like the upper ranges of 680s for 1.4 volts, but it might actually be average or even less than average. I'm not sure. But 1450, 1.4 volts, you'd be looking at about 225 amps through this VRM, producing about 32 watts of heat. That should still be doable. Like, especially if you had a water block, that should be fine. If you don't have a water block, well, you're going to need to put some airflow over this VRM, because 30 watts of heat is not going to dissipate itself through the PCB alone. That's just not going to work. Luckily, you do get, two convenient screw holes right across the VRM, so getting some heatsink on there and then holding it down somehow shouldn't be particularly difficult. So, I'm considering from my perspective of using a universal water block, I'm not actually sure if full cover blocks fit this, because while this does look like it should be reference layout, it's not reference. So, I don't know if this would actually fit a full cover. But anyway, 220 for water cooling, you probably need to put some effort into the VRM cooling here. And on liquid nitrogen, this might be a disaster. So keep in mind that the calculation I use for scaling up scaling up power consumption for GPUs and such, it doesn't compensate for temperature differences at all. So it completely breaks down. Like, it works just fine if the temperature of the GPU core stays at like 70 degrees, 70 degrees at rated power, then 70 degrees it's scaled up, and just keeps that same temperature across the entire scaling range. If the temperature drops by about 20 degrees, you might see about a 10 watt. Well, the thing is that can I do that? No, it's not going to draw on this. Okay, well, the thing is, you have a curve that curves pretty hard right as it goes positive. So basically from like 0 to 70C, you see a bigger change in power consumption than you're going to see any other part of the temperature scaling range. Like, that's the big chunk. Well, actually, it would be like 0 to 100, because past 100 you shouldn't run anything. But you get the idea. If you go much past, like, very quick scaling between 0 and 100, and then below 0 it doesn't really, like, it drops off a few %, but it doesn't really change that much, though I haven't really tested like a full voltage range below 0. So I'm not sure if at higher voltages it might not have more impact, but generally speaking, from the testing I have done, it generally looks like voltage just curves the graph harder. It doesn't shift it around in any way, shape, or form. So the thing is, liquid nitrogen would make this core pull less power than the calculation would tell you it should. At least in theory, because it's not scaling for temperature at all. And I'm not sure if the higher voltage would actually, make the calculation more accurate or less accurate. I'm going to go with less accurate, because the temperature is just way too low for what the calculation was, like, tested against and what I've designed it to deal with. So, yeah. And even for water cooling, this thing, it might be, the calculation might be shooting a little bit high, but, you know, water cooling might be 40, air cooling might be like 70 degrees or 80 degrees. And that is a big drop, and that would make a difference, but it's not as concerning as when the power consumption can literally, in some cases, be cut in half by just going under liquid nitrogen or, well, the one test case the really detailed test case I have, like, you chop 30% off the power draw by going to minus 30 from, like, 70. So 70 to minus 30, you lose, like, 30% of your power draw. And you lose, like, the first 10% in the first 30 degrees, and the remaining 20% that's... Well, whatever. I don't remember. But basically, calculation doesn't work for liquid nitrogen. It should overshoot. So it probably wouldn't actually have to push 361 amps, which would destroy this VRM immediately, because, as I said before, these are 45 amp power stages. This is a 6-phase VRM. This thing is good for maximum output of 270 amps at any temperature, at like room temperatures. Now, technically speaking, there have been people who have liquid nitrogen cooled VRMs, and it does kind of work. The VRM still sucks horrifically, right? Like, the voltage regulation actually gets worse because your capacitors get cold and everything, but at least your MOSFETs don't blow up. But without freezing the VRM, this thing should not be okay for liquid nitrogen or even dry ice, because you probably end up past that 280 amp figure, and at that point, the power stages will probably just go melt down on you internally, because the packaging isn't rated to handle that. The MOSFETs inside probably would. The actual the construction of the MOSFET, the thing that mounts it to the PCB, wouldn't. Though liquid nitrogen tends to, if you make things cold enough, they can't catch fire. They're too cold. But anyway, yeah, so strong, surprisingly strong VRM, but not something I'd want to run liquid nitrogen on, and not dry ice. But for water cooling and air cooling, this is actually, it's decent, And I think that explains why Palit gave this card, because if you take this card and try to overclock it with Afterburner, the power limit slider goes really high. It goes to plus 50 or plus 70%, which is ridiculous. And and honestly, it makes sense. This VRM is a lot stronger than it needs to be for a stock GTX 680. You could have gotten away with a 4-phase of this. Luckily, they decided that they actually want to make a real VRM and not a bloody joke. Even if, this isn't really adequate for extreme overclocking. Now, the memory VRM, don't know the voltage controller. This thing is not, no brand on it. There's no brand indication on this, so putting this into Google doesn't actually get you anything, because there's so many brands using the same numbers. But the MOSFETs for the memory VRM, which is a 2-phase, are a high-side MOSFET from On Semiconductor. This is a 4927. Well, 4927, that's the NTMFS series. And the low-side MOSFET is a 4955. These kind of suck unless you run them on 10 volts. And even on 10 volts, they kind of suck. They have a very high thermal resistance. So, for example, this thing has a temperature difference of 6 degrees centigrade per watt internally. So if you put a temperature probe on top of this MOSFET and measure that the temperature of this MOSFET is 130 degrees centigrade, and it's producing 1 watt of heat, then the actual silicon inside that MOSFET is at 136. Yeah, that kind of sucks. There's MOSFETs out there which have a external case temperature, coefficient of 2 or 1. Well, actually, the 1s are really, really rare, but 2 or 3 is definitely doable, and this is 6. So, not great casing, very high, also high on resistance, pretty slow switching times. Same goes for the low side MOSFET, high on resistance of these on 10 volts. These are 5.6 milliohms, and on 10 volts, these are 7 point something. I've forgotten, and the datasheet isn't open on the right page. Oh no, it is. It's 7.3. But on 5 volts, this is 12 milliohms, which sucks, and that is 8.5, which sucks more. So, terrible MOSFETs, which is why I think this LDO right here produces 10 volts for this VRM, because running these on 10 volts massively improves their efficiency, because they kind of suck on 5. and they kind of suck even on 10, but, you know, they're only powering the memory system, which on a GTX 680 should probably pull around 25 watts. At 1.6 volts or 1.55 volts, ultimately it doesn't really make that much difference to how much current this VRM has to push. And so for stock settings, this should push about, you know, 16 amps at 1.6 volts. That's for 1500 megahertz memory clock. And that would produce about 1.8 watts of heat, which is just fine. Which is why it's fine that these MOSFETs are so terrible, because they don't really need to do a whole lot of work. But if you know, start to overclock the card and, say, hit 1900 megahertz memory, I am still using the same calculation I'm using for scaling GPU and CPU power draw, and I'm not sure it's accurate for memory. I think it isn't. So assuming the calculation is accurate, this would have to push 20 amps, which really isn't such a huge difference in current output, but it does change the power heat output pretty significantly, as these end up producing about 3 watts afterwards. So yeah, you basically get a 50% uplift in heat output from a memory overclock. But again, those two are sunk with thermal pads into, you can see, so those are also sunk with thermal pads into the base plate of the card, so they shouldn't really be a concern either. But basically, because I don't know what voltage controller this is, well, I might try to reverse engineer the voltage control scheme on this thing. I probably won't. I'm thinking e-power the memory, which tends to ruin memory overclocking, so I'll do that after I'm done with e-powering the core and doing good, like, running this thing on liquid nitrogen, because I do plan to go through still go through with that series thing where we're going to go cap modding, volt modding, power modding, and then finally VRM swap. So we'll e-power the vCore first, run that, and then if that does well and doesn't die, then I'll also e-power the memory, and we can figure out some memory current consumption figures with a current clamp on the inputs. So basically, I'm not going to worry too much about ruining the memory overclocking performance. Also, the memory on this is SK Hynix, which should actually clock pretty well and shouldn't complain on liquid nitrogen, so that's pretty good, because some Samsung memory chips, they get cold and they just stop working. So that's not great. But this is Hynix, so that should be non-issue. This LDO up here is probably 1.8 volts for the BIOS. I've not actually bothered to confirm that, but I can't think of anything else that would be in that area of the PCB. I'm sorry for not caring enough. The last thing that Palit's done to make this card a bit more interesting than a bone stock reference, 8-pin plus 6-pin instead of 6-pin and 6-pin. They are still stacked, which I'm going to be honest with you, I think this is the stupidest connector layout I've ever dealt with. It's annoying. It's really annoying. Because, yeah, it's dumb. I'm glad nobody does this anymore, because this is dumb. Though it does make sense why it's done, because if you look at this, right, it does give them the option to basically move this blower fan further to the end, allowing them to accommodate more heatsink. Bam. So, yeah, there's a decent reason for why they stack the connector like that, because if they move that top 6-pin down here, that would move this fan forward a bit, which, yeah, that would kind of not work considering how the shroud's laid out, right? And you actually do need a shroud, like, with this kind of, like, specifically shaped cutout to get good efficiency out of these blower fans, because otherwise they just spray a gentle breeze in all directions, no matter how high you set the RPM, because they're horrifically inefficient fans. What else is there to say about them? Anyway, yeah, that's the Palit GTX 680 that I don't even know the name of, because quite frankly, there's no name on this. It's a 680 from Palit. So, that's that. It's not, you know, it's a surprisingly decent card. I was expecting a reference board which would blow up the moment we put 1.4 volts through it. Because the reference 4-phase, that's exactly what it does. You put it on water cooling, you set 1.4 volts, and unless you have a full cover water block, airflow is not going to stop that VRM from going poof. This shouldn't. This should be actually relatively fine. So that's pretty nice. And yeah, that's it for the video. So like, share, subscribe, leave a comment down below. If you'd like to support what I do here with Actually Hardcore Overclocking, there's a PayPal, a Patreon, and shirts. You can find them all down in the link in the description below. There's also the AHOC junkyard, and I do plan to be dumping a whole bunch of hardware. There's going to be, I want to get rid of the X370 Tai Chi. I'm going to test that board one last time because ASRock put out one more BIOS for it. I'm going to try that out. If it doesn't get any better, I'm throwing it, like, it's getting sold because I want to buy a proper motherboard. Okay, so I need a proper motherboard for Ryzen. So that's getting sold. There's the B350 from Asus. I'm selling that because I bought that for a competition. That competition is over. I'm not going to use that board again, and I'll probably buy a Crosshair 6 Hero. So if there is a Ryzen competition, or actually a Crosshair 7 Hero, because there's going to be X470, so I'm going to be buying that. And yeah, so if there is another Asus competition, I'll have a board for it this time. Won't have to rush out to buy the cheapest thing with Asus's name on it. What else is there? Right. That. Oh, right, and I also want to dump my X99 UD4P and the 5930K. The 5930K is going to be going up very, very light because right now I'm using it for a gigabyte overclocking competition that's limited to any CPU with less than 6 cores. If you have a Coffee Lake and a gigabyte motherboard, that's a really cool competition to join, and you don't have a lot of time. The stage 1 finishes in like the next 5 or 4 hours from when this uploads. So yeah, go check that out. Go check all of those things out. Thank you for watching, and see you next time. Come here, mouse.